Hello and welcome to Quantum Mechanics Made Easy Beginner Problem Playlist. My name is Dr. Jacob Hudis, and in this lesson I'll be discussing the meaning of the wave function and its fundamental requirements. In the Beginner Problem Playlist, I'll solve quantum mechanics problems that are not mathematically intense. In quantum mechanics, psi is the wave function. How do we interpret psi? It's a postulate of quantum mechanics that psi squared dx represents the probability of finding a particle between x and x plus dx. In 3 dimensions, psi squared d cubed r, where d cubed r is dv, gives the probability of finding the particle in a small volume around position r. These interpretations were discovered through experiments. They show that at the quantum level, we can only predict probabilities, not exact locations. This is how nature works at the quantum scale. Asking why it is this way doesn't have a first principle answer. It was discovered through the scientific method. This is the fundamental law of nature. Psi is a wave function and it gives us some predictive power. It allows us to predict probabilities. On this slide, I provide a sample wave function and plot its absolute value squared to illustrate the interpretation of psi. This is a sample wave function. Psi is equal to 1 over root pi sine of 3x. The wave function represents a bound state where the particle exists only between x equals 0 and x equals 2 pi. This is given without derivation or further discussion. The square of the absolute value, psi squared, represents the probability density of finding a particle at position x. The graph shows psi squared of x. The probability density oscillates between 0 and 0.3. This indicates that the particle is most likely to be found at the peaks of the graph. In these locations, the probability wave interferes destructively, meaning the particle will never be found there. If you were to look for the particle, you would never find the particle at these locations. On this slide, I provide the 5 fundamental requirements for a quantum wave function. The wave function must be finite everywhere. The wave function psi must be single valued. The wave function psi must be continuous. The first derivative of the wave function must be continuous, and the second derivative of the wave function must be continuous whenever the potential is finite. Can you explain the reasoning for each requirement? You may want to pause the video and think about it and check if your reasoning agrees with my answers, which I'll provide on the next slide. By the way, this is a picture of me now at age 45, and here's a picture of me when I was 22. And here are the reasons for the wave function requirements. Psi must be finite everywhere. This ensures the total probability is 100% within the region where the particle is confined. The wave function must be single valued. Having multiple values would imply different probabilities for the same location, which is non-physical. The wave function psi must be continuous. Discontinuities would lead to non-physical predictions like infinite or abruptly changing probabilities. The first derivative of psi must be continuous. Recall in quantum mechanics the momentum p is proportional to d by dx, the derivative with respect to x. If the derivative was not continuous, the momentum would not be defined. The second derivative of the wave function must be continuous when the potential is finite. This is necessary for kinetic energy to be well defined and finite. Kinetic energy is related to the second derivative. When I first learned about the requirements for wave functions in college, I was confused. It's helpful to think of an example with classical trajectories. On this slide, there are 2 trajectories, one allowed and one not allowed. In our macroscopic, everyday world, we never see a rock flying through the air and suddenly disappear and reappear elsewhere. We don't need to list properties of classical trajectories because we see them all the time and they follow smooth, predictable paths. We don't see atomic wave functions because our eyes lack resolving power, so we don't have the same intuition. Therefore, we list the properties of wave functions to solve quantum mechanics problems. On this slide, I'll list the requirements for classical trajectories to help you understand why we do this in quantum mechanics. The trajectory must be finite within a given region. The particle can't just go to infinity. Maybe the Incredible Hulk could make that happen, but otherwise it won't. The trajectory must be single valued. This is obvious. The trajectory must be continuous. Particle can't just disappear here and reappear here. That would be really cool if it could happen. I would love to see it, but that's not the way that it works. The first derivative of the trajectory with respect to time, that's called the velocity, must be continuous. Velocity must change smoothly. It can't instantaneously change from, for example, 5 meters per second to 15 meters per second without going through the values in between. The second derivative of the trajectory with respect to time must be continuous. This requirement ensures that forces and acceleration change smoothly as well. And now I'm ready to move on to 3 problems, 3 conceptual problems. Problem number 1. Which of the wave functions cannot have physical significance on the interval shown? Explain why or why not. You may want to pause the video and think about it because I'm going to provide the answers now. This wave function is continuous and finite everywhere, making it physically acceptable. This wave function is also continuous, finite, and single-valued. Nature could choose this as a quantum mechanical wave function. This wave function has first and second derivatives that are not defined, meaning force and momentum can't be properly defined, making it physically unacceptable. This wave function is discontinuous and not single-valued. This wave function has a jump discontinuity and would not be an acceptable wave function. This is an asymptote, so this wave function would go up to infinity. The wave function grows asymptotically, leading to non-normalizable total probability and making it physically unacceptable. And here's problem number 2. The diagram below shows a potential energy function v of x and its corresponding wave function psi of x. Explain why the amplitude and wavelength of the wave function behave as they do in relation to the potential energy function. This is the potential, or the potential energy. It's infinity at 0, and then between 0 and L, it increases at a constant rate until you get to some value of potential, and then the potential goes to infinity again. This means the particle must be confined between 0 and L. This is a corresponding wave function. The wave function has a small amplitude, and the amplitude gets larger as you move out. The wavelength starts out small, and then the wavelength begins to increase. Can you explain why the wave function behaves that way? You may want to pause the video. AcePhysics.org. Math and Physics Tutoring with Dr. Hudis. I'll discuss the explanation on the next slide. The wave function psi must vanish at x equals L, where the potential energy v of x approaches infinity. This is because a particle cannot exist in a region of infinite potential energy. As the potential energy increases with x, the particle's kinetic energy decreases, causing the wavelength of the wave function to increase. A lower kinetic energy corresponds to a longer wavelength. The amplitude of the wave function also increases as the wavelength increases. This is because a larger wavelength implies a smaller momentum, indicating a lower kinetic energy or a lower velocity. Consequently, the particle is more likely to be found in a region where its momentum has a lower magnitude. If it's moving slower, it's going to be in that area for longer, and it's going to be more likely to be found there. And for the final problem, I have 2 potentials drawn, and I ask you to sketch wave functions. Here we have potential equals infinity at x equals 0 and x equals L, and then inside the box, the potential slowly increases up until some value, and then once it gets to this value at the center of the box, then it begins to decrease back down to 0. My question is, can you sketch the n equals 1 and n equals 7 wave function for this potential? Here's another potential. The potential is infinity at x equals 0, and it's infinity at x equals L, and then there's a step function, which means the potential here is 0, but all of a sudden the potential jumps up to some value v0, and then it stays at this constant value for this portion of the box. Can you sketch the n equals 4 wave function for this potential? I'm going to go over the solutions on the next slide. You may want to try this on your own, see if your answer agrees with my solution on the next slide. And here are the sketches of the 2 wave functions. For this potential, E4 corresponds to this wave function as 4 antinodes, 1, 2, 3, and 4. In this location, the amplitude is small and the wavelength is smaller. The reason the amplitude is small is because here it has no potential energy, it's all kinetic energy. The particle is moving quicker in this location. If it's moving quicker, it's going to be less likely to be found there. That means a smaller amplitude. As you move over, the particle slows down. When it slows down, the wavelength increases, and the amplitude will also increase because it will be more likely to be found in that location. For this potential, this is E7. There should be 7 antinodes, 1, 2, 3, 4, 5, 6, and 7. The amplitude is small in this location because the kinetic energy is larger. The amplitude and the wavelength get larger, where the potential gets bigger and the kinetic energy gets smaller. Once again, the amplitude gets smaller and the wavelength gets smaller. The de Broglie wavelength increases as the particle's speed and kinetic energy decrease. This implies the wavelength increases in a region where the potential energy U is larger. A particle is more likely to be found where it is moving slowest. Thus, the amplitude of psi increases in regions where the potential energy U is larger. For a particle in a bound state, there are n-1 nodes and n antinodes. I provided E4 and E7. I did not provide the solution for the n equals 1 case. It would be fantastic if someone could discuss that in the comment section below. Thank you for watching another installment of Quantum Mechanics Made Easy. I'm Dr. Jacob Hudis. Please like and subscribe and check out my website, AcePhysics.org, if you're interested in math or physics tutoring.